There's a direction in space that no human object has ever truly traveled. Not a distant one, not a hidden one. It's right above your head. We've landed on Mars. We've touched a comet. We've flown a camera past Pluto, 3 billion miles from home. And yet directly above the sun, and directly below it, remains in 2026 a near total blank on the map. That's strange because up should be the easy direction. It isn't. And the reason why is one of the more unsettling quirks of orbital physics. A kind of invisible cage every spacecraft launched from Earth is already trapped inside. Today, we're going to break out of that cage. Here's the part almost nobody thinks about. You are not standing still. Right now, this second, the ground beneath you is moving at close to 107,000 kilometers per hour, not spinning, orbiting, racing sideways through space, dragging every human, every ocean, every satellite along with it. Launch a probe from Earth, and it doesn't start from zero. It starts already carrying that sideways speed, which is usually a gift. Want to reach Mars? That inherited velocity does most of the heavy lifting. Nudge the trajectory a little, and the solar system practically pulls you there for free. But try to go a different way. Not outward, not around. Straight up, perpendicular to every planet's path, toward the empty space above the sun's pole. Suddenly, that free velocity turns hostile. You can't just add a little push. You first have to erase the sideways motion you were born with, then build fresh speed in an entirely new direction. Add it up, and the numbers get almost absurd. Reaching Mars costs a spacecraft somewhere around 4 kilometers per second of delta V. The fuel and thrust budget engineers use to measure a maneuver's difficulty. Climbing straight out of the solar system's plane costs something like 30 kilometers per second, nearly an order of magnitude more. Which means, unintuitively, a spacecraft could reach Pluto, 3.5 billion miles distant, for less energy than it would take to hover a few million miles above the sun's own North Pole, the nearest star we have, and it's cheaper to leave the neighborhood entirely than to look at it from above. That's the trap. 4.5 billion years of orbital inertia, and we've never had a rocket strong enough to simply muscle through it. So what's actually hiding up there? We don't fully know, and that's not a small gap. The sun's poles happen to be where some of its most consequential behavior originates. The fastest streams of solar wind erupt from openings near the poles. The sun's entire magnetic field flips polarity roughly every 11 years, in a process that begins at the poles and works inward. In a very real sense, the weather of our entire solar system is set by a region we've almost never looked at directly. We've been watching our own star from the side. Imagine trying to understand a planet's climate while permanently stuck on its equator, never once looking toward its ice caps. Only 2 missions have ever managed even a partial glimpse. The first was Ulysses, a NASA-ESA collaboration launched in 1990. To escape the plane, it took an enormous detour, flying outward to Jupiter first, using the giant planet's gravity to bend its path nearly 80 degrees off the ecliptic, then falling back sunward on a tilted trajectory. It worked. Ulysses gave us our first real measurements of the fast solar wind pouring from the polar regions. But Ulysses carried no imaging instruments capable of photographing what it flew past. We got data. We never got a picture. The second mission is unfolding right now. ESA's solar orbiter, launched in 2020, has spent years slowly tilting its orbit using repeated gravity assists from Venus. In March 2025, it returned something that had genuinely never existed before, an actual photograph of the sun's south pole. Not a diagram, not a model, a picture showing a churning, magnetically knotted landscape utterly unlike the calmer surface we usually see face on. Sit with that for a second. Until last year, the poles of the nearest star in the universe were, quite literally, unphotographed territory. Here's where the mystery deepens. It isn't just the sun we can't see properly from this angle. It's the entire structure we live inside. Surrounding the whole solar system is a vast pressure bubble called the heliosphere. the zone where the sun's outward wind holds back the radiation and particles of interstellar space. Every planet, every comet, every spacecraft we've ever launched exists inside this bubble. Beyond its edge is a harsher galactic environment entirely. For decades, the assumed shape was simple. Something like a comet, rounded on the leading edge where it plows into the interstellar wind, tapering into a long tail behind. It was a reasonable guess, and it made it into textbooks. Then, in 2020, a research team led by astronomer Merav Ofer at Boston University ran new models against updated NASA data and got a different answer. The heliosphere might not have a tail at all. Instead, the shape that emerged looked more like a deflated croissant, a rounded central body with two shorter jets curling off to the sides. Nobody can confirm which model is correct because nobody has ever seen the bubble from outside it. Voyager 1 and 2 both crossed its outer boundary, but they did so nearly level with the planetary plane. A sideways glance, not an aerial view. To actually settle the question, something would need to climb well above the ecliptic and look back down at the whole structure at once. We live inside a shape we can't confirm. That's the kind of detail that sounds like science fiction until you check the sourcing, and it's simply true. So how do you break the cage from Act 1? You can't just strap on more fuel. The numbers don't work. No chemical rocket we can currently build carries enough propellant to brute force 30 kilometers per second of delta V. The answer that's gaining traction among mission planners is almost paradoxical. To climb, you dive first. It's called a solar Oberth maneuver, and the logic runs backward from instinct. Instead of firing engines to gain altitude, you let the spacecraft fall, deliberately, toward the sun, allowing gravity to accelerate it to enormous speed. Near closest approach, potentially exceeding 100 kilometers per second, you fire the engines at exactly that moment. The reasoning traces back to a principle Hermann Oberth described in 1929. An engine burn performed at high velocity, deep inside a gravitational well, converts far more of its fuel into usable orbital energy than the same burn performed anywhere else. Burn at the bottom of the dive, and the sun's own gravity multiplies your thrust for free. The plunge becomes the launch pad. There's a second option being explored in parallel: solar sails. Enormous, ultra-thin reflective sheets, proposed in mission concepts with names like the Solar Polar Imager and the High Inclination Solar Mission, that use nothing but the gentle pressure of sunlight to slowly tilt an orbit over years. No propellant required. Combine both ideas, and you get the leading concept on the table today. A sail spirals a probe closer to the sun. An Oberth burn snaps it out of the plane at the moment of closest approach, and the sail then carries it the rest of the way toward a genuine polar vantage point. Suppose it works. What would a spacecraft actually see floating directly above the sun's pole? The view itself changes. Every planet, including Earth, sits inside a faint haze of interplanetary dust, the debris of billions of years of comet trails and asteroid collisions. You can see it yourself. Right before sunrise or just after sunset, a soft pyramid of light called the zodiacal light rises from the horizon. That's sunlight scattering off this dust, visible proof that we live inside a dirty plane. Climb above it, and within months, a spacecraft would leave that haze behind entirely. A dramatically cleaner sightline, ideal for instruments hunting faint signals like the atmospheres of distant exoplanets, or for mapping the galaxy's structure without local interference. The environment changes too. Above the sun's equator flows the slower, turbulent solar wind, moving around 400 kilometers per second. Above the poles, a faster and comparatively smoother stream moves at 700 to 800 kilometers per second. A different radiation regime entirely. with real consequences for spacecraft electronics. And then there's the big picture. From high enough above the plane, the solar system would finally reveal itself as what it actually is, a flat disk, dust and planets, and the heliosphere's true shape all visible at once, the way we now casually view Earth from orbit. Nobody has ever taken that photograph. Of everything we've imaged across the cosmos, comets, rings, distant moons, a picture of our own solar system from outside its plane is still the one that doesn't exist. So here's the question for you. If you were designing the first mission to actually climb above the sun, would you trust the patient solar sail or the violent gravity-assisted dive? Drop your answer below.